Hello everyone, today we start with range attacks, and the good news is we have almost everything we need for ranged attacks already available. Because we're going to use this somewhat ill-chosen name MeleeAttackAction also for a ranged action. So the first step will be to rename this one from MeleeAttackAction, because these refactoring functions in Xcode aren't always. Okay, well, let's see. Then we also have these as a name in many places. So let's just try and find them. Look, this one didn't get updated correctly. And this one either. This is going to be tedious. This is a melee attack action. That one actually can be called as such, just because we want to show an animation that really looks like a melee attack. So that one we can keep. Then we have our tests. The first part of the test is all about melee as well as attack actions in general. So we can rename this thing like this. And here I guess we need to search and replace them all. So let's find the next one. Replace. That's not okay. So let's find the next one. Replace, 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 and the same for the one that starts with a lowercase. So let's replace, and let's hope this one still compiles. We might have forgotten somewhere. Okay, so this is going surprisingly well. Okay, so the test succeeded. Let's see if we can find the word melee attack action. Well, only on the game scene, and those are the ones we did look at. So this is okay. So we now have a general attack action. Let's make sure that we can also do ranged attacks. So in our action tests, let's create a new section for ranged attacks, and let's test an attack action make does not return nil when within ranged attack range. So imagine that we have something like a range of 3. If we have a target within 3 range, then we should be able to create an attack action that targets that entity. So we need an attacker. I think we can use some of the stuff we have here. So let's see. But this time we place this one a bit further away. Then we can have a maybe attack action. That's an attack action we make in our example map for our attacker, targeting our target's position, and we pass in all the entities, the attacker and the target. And then we assert not nil the MeleeAttackAction. So let's run the test. And the test fails. Let's make sure we get it running. So let's also open our action and make sure that we have we're able to get an attack action back. Now what we could do is we could simply comment out the check on reachable tiles. However, if we do that, this test will pass, but now another test will fail because this one tests what happens if you target something outside of range. So that clearly is not the solution. So let's put this one back. What we need to do is calculate the reachable tiles a bit different. So here we just use a neighbor's map. Let's use a Dijkstramap targeting our entities position.xy, and then we can return our Dijkstra, we filter where the value is less than our entity's attack range. So now we also need an attack range on our entity. For now we can just hard code in a value. No, that's not such a good idea. We'll make sure that we can set it through the initializer, and we default it to 1, so that makes it a melee attacker by default. Okay, so now we have an attack range here that we can filter on, and then we can map to convert to 3D. And we can get rid of this code, and we need to take the keys because of passing in a dictionary that maps coordinates to cost values. So let's run the test again and see what happens. This test still passes because I now need to give our entity an attack range. So let's give it an attack range of 3. Let's try again. And now the test passes as well as the other one. So the melee attacks also still work. So that's a good start. Let's see if we can also see this happening for our for the entities in our game. So let's give our rogue an attack range of 3 and build and run a program. So let's see. So let's move our rogue. We can see how far we can reach with our bow and arrow. So we can execute the attack to this one. We don't have an animation yet. That's why it looks so bad. But indeed, it attacked the knight for 3, and we saw the hit animation after him. So we're quite far already. However, notice that now the rogue is not facing the knight, and the knight is not facing the rogue. So clearly we're missing something, and I think we should just create a test to check this situation as well. So we do a test. We can actually copy paste the one above that tests for the facing each other after the attack, but this time for ranged attack. So we place this one at a slightly different position, and let's run these tests. and this one fails. And the reason for that is when we go to our action, we complete, and here we try to determine the attack direction, and we use the rotation from look direction to do so. And this one currently looks at vectors with a length of exactly 1 in the Cartesian directions. And otherwise it takes the attacker's existing rotation. To fix this, we need to make our rotation a bit more sophisticated. We should make it so that it works also for vectors that are passed in that are longer than 1, and also ones that aren't exactly straight. So let's give an example. So this is what we currently have. We have vectors 1 large, and those get translated into degrees or into rotations. The first step is I want to at least make sure that I can also have arbitrary length vectors also being translated, and then I also want to be able to sort of find the one that is closest. So if we have a vector that's not completely going either in the x direction or in the y value, then I want to take the one that's most similar. So that means that we need to do some work on our rotation. So let's open rotation, and also let's open our rotation tests, and let's start by creating a new test. From look direction returns correct rotation for Cartesian vectors of length longer than 1. And these tests are failing because we're getting nil back. So let's change our rotation, and what we're going to do is, it might sound a bit sophisticated, but I'm going to use dot products to determine which vector is the most appropriate, because the dot product between two vectors describes how similar they are. And that means that we need to implement a dot product in our vector 2D, and that requires two things. First, we need a length, and the length will be based on the Pythagorean formula. Then, using this, we can create a function called dot normalized that takes in two vectors, a left hand side and a right hand side, and this returns a double. And we need the length to normalize these vectors, so the length of the left hand side will be left hand side dot length. Similar for the right hand side. And then we can calculate the x part of the dot product. This will be a double of our x divided by the left hand side dot length times a double of the right hand side divided by the right hand side dot length, and something similar for the y part. And then we return the left part plus the right part. So now we have a dot product. Let's use it in our rotation. So this from loop direction stuff we can get rid of. We're going to do this different. So we take let rotations and dot products. We'll take first an array of rotations. We'll take all we have. Then we map these to the dot product. So we'll use our new dot normalized function, and as the right hand side we'll use the direction that was passed in, and for the left hand side we want this one, but in the form of a vector, and that requires something like 2 vector 2d function, which we don't have yet, but we'll add it. 2 vector 2d, this returns a vector 2d. We switch on self. Add the various cases, and here we return a vector 2d for 1 and 0, and we can just copy paste and make sure that we choose the right values. So this will be 0.1, this will be -1 0, and this will be 0 -1. So now we should be able to get ourselves, if we look at the type of this thing, oh, we can't see that yet, that's too bad. Anyway, we should be able to get a dot product here. And then what I'll do is I'll return a tuple that takes a rotation and its dot product. That's the dot product we just calculated. And now this one has a type of rotations and dot products. And what we'll return is the one with the highest dot product. So we'll maximize comparing the dot products between 2 entries in the array. And then we return the rotation. And we can get rid of this. Let's see if this builds and if the tests run. And now the test passes. However, a different test fails. And this one, that's this one, the from. Loop rotation returns nil for a 0 vector. Basically, you always get back 1 if you do this. I don't think that getting a rotation from a vector with a length of 0 makes any sense. So what I'll do is I'll first check that the direction.length is larger than 0, else we return nil. Because I can't determine a rotation if there's no direction. Okay, now all these tests succeeded. Let's see if this also works for rotations with other types. For non-Cartesian vectors. So let's create some. So let's say this becomes 2, 4, or 6, 3, or -2, -4, -9, and 4. And run the test again. And these pass. Let's see if this also works in the game. So let's move a bit. Let's attack. So we still don't have the animation, but at least afterwards they're looking the correct direction. Let's see if we can also let's see what happens if I move here. So they're definitely not face each other. I'm going to attack the knight, and now they end up facing each other as well. So this works. That's the end for this time. Next time we'll add an animation for the ranged attacks. So then the rogue can really shoot the bow and arrow. And that's it for this week. Thanks for watching and have a good day.